Talk. So it's my pleasure to introduce Wessel van Woerden, who will talk to us about lattice packings and perfect lattice.
Okay. Thank you for having me. So I will start with a bit of a visual introduction before we get to the real definitions. And this topic is very nice because it's very geometrical. So let's start with the problem. The sphere packing problem. Most of you probably already know it. The question is, how can we pack identical spheres in a space such that the density, or if you look at balls, like solid balls, that their density is maximized. And as you can see, this problem is very unstructured. However, the solutions, the optimal solutions, are not. So on the left, we have the optimal solution in dimension 2. Also known as like the hexagonal packing. And on the right, you see the optimal solution in dimension 3. However, we don't know much more than that, because it's only solved in dimension 2, 3, 8, and 24. And 8 and 24 are, of course, from the E8 and the Leech lattice. And what makes this problem hard is the lack of this structure in the problem statement, basically. So what we can do is we can constrain this problem a bit by looking at so-called lattice packings. And here we have the extra constraint that the centers of all these spheres must form a lattice. And this makes the problem significantly easier. And that's why it's already solved up to dimension 8 and also 24, of course. So given a lattice, you can always create this packing by just making these spheres given them radius half times the minimum distance between 2 points. And if we look at this problem as kind of an optimization problem, then our solution space is the space of all possible lattices. And if we don't care about like rotations or like orthonormal transformations, then one way to represent this is as positive definite quadratic forms. And in fact, these form a cone. So this is kind of every point in this space will give you a lattice packing. And because we don't care too much about scaling, because given a lattice packing, if you scale everything up, the density stays the same, we will now look at only those lattice packings that have spheres of radius at least 1. And what you then get is the so-called Ryshkov Polyhedron. So all the points inside of this polyhedron correspond to lattice packings with spheres of radius at least 1. And everything about this polyhedron is infinite. Like you have an infinite number of facets. I can only show you a finite amount of them, but you have an infinite number of facets. You have an infinite number of vertices. And when you have this restriction on the size of the spheres, the only thing that's left to do is to minimize the empty space around these spheres. And in fact, if you give like the function of the amount of empty space, then this is a concave function in this cone. And so we get a concave minimization problem over this polyhedron. And from this, we know that the optima lie at the vertices. But I just told you that we have an infinite number of vertices, so this doesn't seem to help that much. However, most of these vertices correspond to basically the same lattice packing. So we have some notion of similarity that two lattice packings are basically the same. And under this notion, there are only a finite number of really non-similar vertices. Okay, so let's use this to solve the lattice packing problem in any dimension. We just fix our dimension. Later we will talk about how many of these classes we have. So how do we solve the lattice packing problem? Well, we just enumerate all these non-similar vertices, and we pick the best one. That's it. And this is exactly what Voronoi's algorithm does. What it does, it starts at like a single vertex, and then it finds all the neighboring vertices. If this new vertex is already like similar to one that's already been found before, then we just discard it. If it's a new one, then we continue this exploration. And actually, if this at some point this will finish, because you only have a finite number of non-similar vertices, And you can also prove that if this finishes, you like the algorithm gives a proof that you actually have found all of them.
Stupid question. So if the function is convex, you said.
Concave. Yeah.
So why do you need to explore all the vertices? Can't you just keep moving in the right direction?
No, it's the wrong direction. You're minimizing a concave function, right? Minimizing.
Yeah. So normally, if it's like you're maximizing, then you can.
Yeah. Okay.
It's somewhere the solution is somewhere in the center or something, and you walk through it. Yeah. And I won't go too deep in. Like in the next talk, Achu Schumann will go a bit deeper in how to actually run this algorithm. But I want to, if you like algorithms in any way, you're going to be very happy with this thing because it involves for lattice problems like shortest factor problems, lattice isometry, lattice reduction. In the field of computational geometry, for example, you need to solve the dual description problem. And also, to make this feasible, you need to abuse a lot of symmetries. And for this, you also need to do a lot of group computations in like permutation groups. So compute stabilizers, orbits, and all those kind of things. So you need a lot of algorithms to actually do this. Okay. Now we get to the real definitions. So the space we're working in is the space of real symmetric matrices. So D will always be the dimension of these lattices, or of like lattice packings. And this space itself has a dimension n equal to half times D plus D minus 1. And this is just the amount of coefficients on like an upper triangular matrix, or like the upper triangular coefficients. Okay. Now, in order to make these nice pictures, we need some kind of geometry on this space. So we define the following inner product. And this is known as the trace inner product, but if you don't care much about it, it's just if you take this matrix and you collapse it as one big factor, then it's just the standard inner product. Now, if you have a symmetric matrix, you can define a quadratic form by just saying, looking at x transpose times q times x for a vector x. And the nice thing about this inner product is that this thing has a geometric interpretation. Namely, this value is the same as taking the inner product with q and x outer product x for these vectors x. And as a result, if you take a fixed vector x and you look at all quadratic forms that take a certain fixed value on this x, then they all lie on one hyperplane. And if you take all quadratic forms that have value at least something, then you get like a half space. And for a positive definite quadratic form, so these are the ones in this cone we saw earlier, we can define some nice properties, namely the arithmetical minimum, which is just the minimum value it takes on all non-zero integer vectors. And what are these vectors? We call them the minimal vectors. We denote them by min q. Okay, so how does this correspond to these lattice packings? Well, if you have a lattice with a certain basis B, then you can construct a positive definite quadratic form by just looking at the gram matrix of this basis. And what's the density of like a lattice packing, given if you look at the lattice? Well, we can just look locally because it's just repeating better. And then the density will be the volume of this ball divided by the volume of this Voronoi cell. So, and the first one is proportional in some sense to this arithmetical minimum, and the second one is proportional to the determinant. And we care about the ratio, and we call this this is known as the Hermite invariant, and this is directly proportional to the density of this corresponding lattice. So instead of working with lattices and lattice packings, we just care about quadratic forms, and we try to maximize this ratio, and this is known as the Hermite Constant. Okay. So now we get back to this Ryshkov Polyhedron. So for a fixed lambda, we want to only consider all those quadratic forms that have a arithmetical minimum at least lambda. And this corresponds exactly to like lattice packings where the spheres have a minimum size. And another way to describe this is that for every non-zero integer vector, these quadratic forms must take value at least lambda on them. So for every non-zero integer vector, you get this half space by this nice geometric property. And the Ryshkov Polyhedron is just the intersection of all these half spaces. So important to note that every facet of this Ryshkov Polyhedron corresponds exactly to one of these non-zero integer vectors.
What denotes your notation in bracket Q and X, XT? What does it mean?
That's the inner product I defined before.
Yeah, it's X transpose QX.
This inner product. But I mean, what we use is this.
Yeah, yeah.
The value they take is the same as you can. Everything is geometry basically. Okay, so every facet is a non-zero integer vector. And now the optimization problem becomes somewhat easier if we restrict to this space, because we only have to minimize this empty space around it that's left, and that's exactly given by this determinant function. And by Minkowski, we know that this function is concave in this cone, and so the local optimal at vertices of this Ryshkov Polyhedron. Okay. What are these vertices? Well, these are the ones that we call perfect forms or perfect lattices. And yeah, the easy definition is just to say, okay, Q is perfect if and only if it's a vertex of one of these Ryshkov Polyhedra. And note that the minimum, the number of minimum vectors of such a perfect form is at least n up to like 2 times n, because you have plus and minus x. And that's the case because every vertex is adjacent to at least n, which is the dimension of the space, facets. And these are exactly also the minimum vectors of this perfect form that lies at the vertex. Okay, now a quick note about the similarities. Well, if you have a lattice basis B, and you have a basis B times some unimodular U, so it's just basis transformation, then we know that they generate the same lattice. And we can do something similar for quadratic forms, but then you get this U transpose Q U as the.
In the last slide you had 2n, but with symmetry you will only get n, right?
Yeah, so you have like, if x is a shortest vector, minimal vector, then minus x is also a minimal vector, but x and minus x give the same facet.
They both define the new vector.
The same, yeah.
It's XX transpose.
X transpose is the same for plus and minus x.
Should be S or D, right? Not G or D.
Yeah.
No, it's the same thing because they're invertible.
Yeah. Oh, right.
Oh,
Yes.
Z.
Yeah.
Maybe they can have minus one.
Determinants.
Yeah.
Okay, and what's nice to know is that these like arithmetical minimum and determinant are what you would expect, like they stay the same under this transformation. And we want a slightly broader notion of similarity because we don't care about scaling. Okay, so now a nice question would be like, how many of these perfect forms or how many of these non-similar vertices do we have? So if you would start running this algorithm, you would, if you want to have any sense of how complex this algorithm is, at least you would want to know how many of these things you have to enumerate. So what do we know? Well, we only know all the perfect forms up to dimension 8. For example, in dimension 2, which is the one I showed all these pictures for, because then in dimension 2 the n is 3, which is all the pictures I showed. And you see that we have only one non-similar perfect form. So actually all these vertices you saw before are the same, or they are the same up to like, a basis transformation. But if we go up in dimension, we see that at some point, the amount of them quickly increases. So only in 2005, Mathieu de Tour and Arthur Schumann there and Frank Valentin, they succeeded the enumeration in dimension 8. And thereby also proving Lattice packing theorem, but that was already proven before. And in dimension 9, they found more than 500,000 of these. And during my master's thesis, I also tried to improve these algorithms a bit and found more than 23 million, but still with no end in sight. Like, they're probably way more.
So the answer, not the number, but the answer to the problem, the perfect, the optimal solution in dimension 8 was already known.
Was already known.
Well, in dimension 9, this part of the computation that was being done to try to find the optimal solution.
We already think to know the optimal solution.
But it's
no, and like the thing is, you during this enumeration you find the optimal solution pretty quickly in like years, for a lot of reasons. But you need to finish this whole enumeration to know for sure that you haven't missed any. So that's kind of the.
Also in higher dimension, you can find good candidate.
Yeah, there are ways to, like, you can, instead of doing the full enumeration, you can do like a random walk on this graph, and then you also find pretty good.
What is the highest dimension when you can start running this program? When you not complete, but just.
When you can start, I mean.
Just to start until you
Oh.
find a reasonable.
Yeah, I mean, that depends. Usually you need to solve like lattice symmetry and also, or that's not that important if you just do a greedy walk, but shortest vector problems. And then you need to do this dual description. But I think if you can solve the shortest vector problem
Which in
a bit
dimension,
quickly.
for example, is easy. So yeah,
Yeah.
you can do
You can run this in 24, but you can run this in 24. That's no problem. But you're not going to be able to do any full enumeration.
exploring the full space.
Okay. So what do we know in terms of how many of these things we have? So let's call PD the number of these similarity classes. Then the known bounds. Okay, so in 1998, Christophe Soulet proved an upper bound exponential in d to the 4th log d. And he used this also to say some nice things about the Van de Vee conjecture in number theory. And pretty recently, Roland Batcher gave a constructive lower bound exponential, single exponential lower bound, and an upper bound exponential in d cube log d. And in this talk, we will give a nice geometric proof of that gives an upper bound exponential in d square log d.
We have some intuition for, so like this is like thinking of, I don't know, a matrix of d squared entries of size.
Yeah, so the space is already like of size d squared.
Yes.
So this could well be tight.
I see. Like this intuitively makes sense.
This intuitively, yeah, also already in for example the paper of Roland Batcher, he already gave a lot of like heuristic reasons why this should be the upper bound, but yeah, no idea for a proof. And also, if you see this list, then I mean, okay, it's very small sample size, but it makes it's more than single exponential, at least you would say. Okay, so what's the idea? Well, suppose you have a cone, and inside of this cone you have a polyhedron. Then at each vertex, you can create the so-called outer normal cone, which is just for every facet you have a normal, and you take the cone generated by these normal vectors. And note that if you have two of these vertices that are next to each other, then these outer normal cones fit nicely together. So what we just do, we create all these outer normal cones, we grab them together, and that's what you get on the right, and then we just flip it upside down for whatever reason. And what you see is that this polyhedron gives, in some sense, a subdivision of this cone on the right. And we have a little bit of space left in between here, but that's just for any vertex that's yet to come. And we can do exactly the same with our Ryshkov polyhedron. So at every, like, let's say we have this vertex, then you have the three facets around it. each of them gives a normal, which corresponds to these minimal vectors. And then you take this cone, and we look at all these cones from above. So you first grab them together. And then, for example, this vertex corresponds to this cone, and this vertex corresponds to this one. Let's see. Okay, what are these cones exactly? These orthonormal cones, these are so-called Voronoi domains, which are just, if you take a positive definite quadratic form and you take the minimal vectors and you look at like x transpose of these minimal vectors, and you just take the cone that's spanned by these things. And this cone is only full dimensional if and only if Q is perfect, which makes sense because you only get a full dimensional outer cone at vertices, like if you're at a facet or an edge, you don't get a full dimensional normal cone. And I quickly want to go back to this picture because this is exactly the picture that kind of gave me the idea for the proof. Actually, the same picture is in the book by Lattice Sherman about this topic, and that's what sparked the idea. So what we see is we have all these Voronoi domains. However, it's clear that we can't fit many of these, some of them are large, and we can't fit many of these large ones inside of this cone. But in dimension 2, we also saw that actually all of these Voronoi domains correspond to the same lattice packing up to like this basis transformation. So what if we can, in every similarity class, we can find at least one representative that has a somewhat large Voronoi domain? If we do that, then we can't have that many similarity classes. That's kind of the intuition. Okay, so this, in more concrete terms, we have an upper bound on like the size of this cone, and we want to find a complete set of representatives such that these Voronoi domains are lower bounded in some sense.
So, excuse me, large means large. Normal cone is large. What?
The Voronoi domain, yeah. So, yeah. So I will quantify this, but in some sense it would say like, okay, if you have this upper bound, this lower bound, then the number of classes can be is at most this upper bound divided by this lower bound. And of course we need to like these cones are infinite, so can't just talk about volume. So for this we just put a cap on them. So we restrict ourselves to the following half space, which is just we bound the trace by 1, which is nothing more than just this flat cap. And if you do that, then we don't have to worry about the volume of this cone. It's totally small. Okay, so very quickly, what's the volume of a simplex? Well, you can just in n dimensional in dimensions. It's 1 over n factorial times the determinant of all the pairwise, like the gram matrix of all these spanning vectors. Okay, so these Voronoi domains, they are spanned by these minimal vectors, these x transpose, but we have put a cap on them, so we need to normalize by the trace, and the trace exactly x transpose x. That's easy. So what we then get is these simplices. They don't necessarily have to be simplices, but we only try to lower bound the volume, so we can assume that they are simplices. Yeah, so these are just the normalized rays given by these minimal vectors. Now we can just compute the volume. That's not so hard. So you get this maybe ugly thing. But what we can do is we can just take these normalization factors out of them. So we get this product of the normalization factors in front. And now all these vectors are integer. And as a result, these inner products are also integer. And so we have a determinant of an integer matrix. And we know it's non-zero because these things are full dimensional, so they can't have volume 0. And so this has to be at least 1. And so we remain with this thing, and we want to find some set of representatives such that this is always lower bounded. And we immediately see that for this we have to upper bound the size of these minimal vectors. And that's where the following slightly technical lemma comes in. I won't give the proof, but and this lemma just says, okay, we can find such a complete set of representatives for which these minimal vectors are of polynomial size in the dimension. And for a proof, this uses transference theorems and dual lattice reduction.
This is a statement about the size of the coordinates of a short
If-
vector, some basis.
Yeah, precisely.
So you're saying that you can have some basis that has polynomial coordinates for all short.
Okay, and I mean now we can just plug this in, and we get that the volume is at most this thing, which we choose as our lower bound. Well, and then we are basically done. Number of these similarity classes at most the upper bound if I have lower bound, or the upper bound we didn't need to care about, it's small, and the lower bound if you write it out you get this. And now remind yourself that this n is quadratic in the dimension, so because of this n factorial and this n in the exponent, you get exactly this exponential in the square line. And that's it.
I don't know whether this makes sense, but is it possibly true that the x's that define a vertex, especially for the optimal vertex, don't have very high coordinates, bound depending only on d? Now that may not be true for all q, but maybe q's that themselves have small rational entries.
So you can restrict your search space, you mean? Or?
So that you can restrict the number of x's that can possibly arise.
Yeah, could work. Maybe. I haven't thought about it.
Do you have any ideas for lower bound? Like a better lower bound?
I mean, either you have to do some constructive proof, but I have no direct ideas for that. If you want to turn something like this in a lower bound, then there are a bit of problems. Like you, for example, at some point you just assume, okay, we assume this is like a subcone, that's just a simplex, but of course this thing can be much larger. And also, now we only need to find like one big representatives, but if you go for the lower bound, then you kind of need to know the size of all Voronoi domains that correspond to one class. So you might be able to say something about, I mean, you know that a lot of them, at some point they have to decrease because otherwise they can't ever fit in this cone. If you can get like some expression that describes this, then.
My question is kind of similar. You said that there's a heuristic saying that your upper bound is probably close to the truth. Can you explain that heuristic again?
I mean, in global sense, it's just like the space of the solution space is of size d squared. So it wouldn't be like, in that sense, it's not too surprising that you get something exponential in the solution space you're working in. But that's of course like no real argument. The other heuristic is just we find a lot of them, so it's. But yeah. Now, if you, I think if you in the, I mean, I did this a few years ago, so it's not all the details are not really there anymore. But I think in the paper of Roland Batcher, that's on my it's in the dissertation. So the paper by Roland Batcher, I think, like he tries to give some heuristics why this should be the upper bound,
Including the log d in the exponent?
why you need it, or.
No, is that like also in the heuristic? Or?
No, I mean you might be able to. No. Like so with this proof, not. I mean it's you get this n factorial, which already gives you already gives you this log and exponent. There might be some way to get rid of it, but I don't find it very weird to get a